we will discuss the free particle solution of Dirac equation. And we know that the free particle solution is a plane wave, so it is also known as the plane wave solution of the Dirac equation. And the Dirac equation for a free particle is that this is the Dirac Hamiltonian, as you know it, C alpha dot P plus beta mc square, and there is no extra potential, external potential, so V equal to 0, and in the right hand side it is E equals IH ka del del T, the time dependent operator part of the energy. So as we know that for a plane wave, a function, this psi, in fact, just a bit of caution that use this psi here. It is just a typographical mistake kind of by me. I use this big psi actually for the complete solution. So these two are actually same, and use this one. So psi RT, this has a part, this is actually a radial dependence part written as a psi depends on P, because if the momentum of the particle changes, then this will take a different form, then this part changes, and the oscillatory part e to the power IP dot R minus ET by H cut. This is all known to you. I just tell you to focus on this part because the free particle, it is actually denoted by its momentum. So the time independent part here, will actually depend on P. So if the momentum changes, then this function will change. So it is actually written as psi depending on P, but it is written in the position coordinates. Don't mix it up. Now this equation, say equation number 1, as it involves alpha and beta who are 4x4 matrices, so your psi must be a 4-dimensional column vector, which is known as a Dirac spinor. This is a very important term, Dirac spinor, only spinor in fact. You write psi is a 4 component, psi 1, psi 2, psi 3, psi 4, and you know that we actually use alpha and beta matrices we have written in our previous classes in actually 4 blocks. If you remember, alpha matrices are written in 4 blocks, and in each block there are 2x2 matrices. These are sigma Pauli matrices, Pauli spin matrices. Here there are identity matrices I and null matrices 0. All of them are 2x2 matrices. So we divided them, alpha and beta matrices, in 2x2 blocks. This is alpha x equal to 0, sigma x 0, and so on. So we use psi as a combination of 2 component spinors, phi 1, which involves the upper part of psi 1 and psi 2, and the lower part phi 2 as psi 3 and psi 4. So you write psi as phi 1 and phi 2. It looks like a 2 component vector, but each component phi 1 itself is a 2 component vector. Now we use the equation 1, we replace beta by the form given and alpha by the form given here, and then we expand the equation. So our mc square beta minus IH cut C alpha dot P phi 1 phi 2 equal to IH cut, and so on. So you just carry out this integration and then expand it, carry out the calculation, matrix calculation, and expand it. So it comes out to be a coupled equation, 3 and 4. Each term is involving phi 1 and phi 2. They are coupled equations. Now for the case of simplicity, as we will not need this IH car del del t operator anymore. In fact, in the previous, in the initial phase, we could have written simply E psi instead of this one, but I have written this T part just to make you aware of this kind of solution. You just can continue with E here and P here, in fact. So using P and E, we write equation 3 and 4 in a structured form this way, and then rearrange it to find the T minus mc square phi 1 is C sigma dot P phi 2, and the plus mc square this way relates phi 2 and phi 1. And just then a mathematical manipulation, multiply by E plus mc square, multiply equation 6 by E plus mc square, and you will see this one, and E plus mc square phi 2, this is the number actually, you know, and this E plus mc square phi 2 you replace C sigma dot P phi 1, and so you obtain an equation in terms of phi 1. This is actually the right hand side is operator and the left hand side is a number, in fact. Now you expand sigma dot P, sigma x P x, sigma y P y, sigma z P z whole square, do a simple algebra, use the commutation, anti-commutation rule of Pauli matrices, and then you find that sigma dot P square equals P square, as simple as that. So your equation becomes E square minus m square C power 4 phi 1 equal to P square C square phi 1. This equation 8, simply write P square here. And you bring it back here, so E square minus m square C square minus P square C square, m square C4 minus P square C square phi 1 equals 0. Now this part must be non-zero, otherwise your phi 1 will be 0 and it will give you no solution. And as we have multiplied by E plus mc square, the equation 6 was multiplied by E plus mc square. You could have done it other way around. You could have multiplied equation 7 by E minus mc square. No change would be there. You check it. This is my advice, that you check it by multiplying the other equation by E minus mc square and arrive at the same point. And in that case, you will find that phi 2 will become 0. So if phi 1 is not equal to 0, then your E square minus m square C4 minus P square C square must be equal to 0, and hence E equals plus minus this one. This is a known result, known relativistic result for us, but it gives us two solutions. E equals plus this one, plus P square C square plus m square C to the power 4 to the power half, and minus of this one. So we name them as E plus as the plus component, E minus as the minus component. So we see that the energy of a Dirac particle, you note this part, this is important, very important. In fact, we will see it in the next class. This part has extreme importance in the field of physics. Actually, this this algebra, this part led to the prediction of antiparticles. We will see it in the next class. So for E plus, you see that the minimum energy is mc square. If you set P equal to 0, if you consider the particle to be at rest, then E equals mc square. This is the minimum energy, and if your P increases in any direction, because it is P square, so if your mod P increases, then the energy increases. That's quite natural, because kinetic energy increases in that case. And for negative E, you see the starting value is minus mc square for P corresponding to 0. For the free particle, the negative energy is minus mc square, and again it becomes more negative if your P even if your P increases, that is your mod P increases, and P increases in any direction, the negative energy becomes more negative. That's a very striking feature, in fact, of this calculation, but still we have to go ahead with it. Now we continue that we had this one phi 1 equal to this one, and we see Say in our case, if P equals 0, then the positive energy becomes mc square. So in this case, if you use positive energy here, then it will be mc square minus mc square. So your phi 1 will bounce. Therefore, this E in the denominator, this must be E negative. I repeat this part. If P equals 0, then this part becomes 0, the denominator becomes 0 if you use the positive energy. So to protect this, you must use the negative energy here. That means you must use E minus here. You see, I have written E minus here, just to protect phi 1 from diverging. Now, as E minus is actually negative of E plus, so we use the form of E plus everywhere. So phi 1 is negative, minus, this minus comes out, and in the denominator it becomes positive. So the phi 1 becomes this one, and in a similar fashion for phi 2 you must need to use the energy expression as E plus. If in case of phi 2, if you use phi E minus here, then the denominator will bounce, denominator will be 0 and phi 2 will diverge for P equal to 0. So your solution must correspond to the general case and acceptable for every value, for acceptable for every case. So you must use E plus in the denominator in case of phi 2 and E minus in the denominator in case of phi 1. We have just done a mathematical operation in case of E minus and imported a negative sign so that we can use E plus in both the cases. Therefore, phi 1 corresponds to the negative energy solution. Phi 1 corresponds to the negative energy solution, phi 1 and negative energy. Here, phi 1 E minus. This is the part. Check it. Phi 1 is the negative energy solution and phi 2 is the positive energy solution. So we see that in fact there is a comment to make here. As we have seen that there are two solutions actually, phi 1 and phi 2. So what is the weightage of them? What is the magnitude of them? It can be seen that in non-relativistic limit for positive energy solution, this equation 2L for phi 2 is a small magnitude as compared to phi 1. And phi 1 is thus known as the large component and phi 2 is the small component. I don't tell you to focus much on this. You just know that there are two components depending on their contribution in non-relativistic limit. Phi 1 is known as the large component and phi 2 is known as the small component. When needed, if needed, in case of actually it comes into play when we deal with the hydrogenic solutions or atomic solution for atomic orbitals, then they comes into play. Right now we just know the names and don't focus. And for negative energy solutions, large and small components are just reversed. Therefore we have seen that equation 11 and 12, that means for phi 1 and phi 2 has two possible solutions, as both phi 1 and phi 2 are two component spinors. Two possible solutions, that they are two linearly independent, phi 1 and phi 2 are linearly independent and they will have two component spinors in each case. Now as we know, what are the shapes of phi 1 and phi 2? Now therefore we look back to our knowledge of angular momentum, where we used two component column vectors. We used them previously, 1 0 and 0 1. we used them as the eigenfunctions of Pauli spin matrices sigma x, sigma y, sigma z, and these sigmas are important in this algebra also. As we know, just a recapitulation, this 1 0 and 0 1, these column vectors, eigenvectors, they corresponded to the j equal to half case, where only the spin half of the particle was considered, and as sigma z equal to 1 0 0 minus 1. This is our form of sigma. This is our form of sigma z. So we knew that when sigma z acts on 1 0, it gives us the plus 1 eigenvalue, and when sigma z acts on 0 1, it gives us the minus 1 eigenvalue, and for this reason the 1 0 is known as the spin up state. We all know these things, and 0 1 is the spin down state. So we have 4 possible combinations, One is E plus, positive energy spin up. We use E plus, and then we use 1 0. Positive energy spin down, negative energy spin up, negative energy spin down. In such way we can arrange the solutions, and we see that there are degeneracies, because this E plus and E plus spin up and E plus spin down, they are positive energy solutions. We term them as noted psi A and psi B. This is just naming. We name them in this way, say. And similarly, E minus spin up and E minus spin down, we assign them in the names of psi C and psi D. Now, as we know, sigma x equal to this one and sigma y, we know the shapes of Pauli spin matrices. So these are our known things. Sigma y equals 0 minus I 0. So we calculate sigma dot p, because sigma dot p appears here. This is our sigma dot p in both in phi 1 and phi 2. Both in phi 1 and phi 2 we have sigma dot p. So what is the shape of sigma dot p? If we expand it, so we will found that simply this one, and use the sigma x here given, sigma y here given, and sigma z here given. So you will find out this matrix, this operator for sigma dot p. This is a 2 by 2 operator. And now let us consider phi 1. If phi 1 is 1 0, then phi 2, this is from equation 12 and given here. So use sigma dot p matrix into 1 0 and expand it to find out phi 2 as c by e plus mc square pz by px plus ipy. A very simple thing. So your entire psi a, E plus spin up is psi a, as we named it, is a 1 0. This is the psi 1 part, phi 1 part, and this is the phi 2 part. This is the phi 2 part. So this is, and in 1 is the normalization constant. So this is your psi a, which corresponds to positive energy spin up condition of the electron. Now you use positive energy but spin down, so psi 1 is 0 1, and you now know how to calculate it. Use phi 2, use this equation, and then phi 1, the structure. So this will come out as n2 with n2 normalization condition constant, and your as this one is your phi 1, and this comes out to be your phi 2. Now we obtained both the positive energy solutions. Now the negative energy solutions is E minus, as simple as that. Use phi 2 1 0, and then phi 1, you obtain phi 1 from this equation. Use this equation to obtain your phi 1 and use phi 2 as this one. As simple as that, and then you obtain the expression for psi c, and then in a similar way this is your E minus spin up, and if you consider phi 2 as 0 1, then you will get E minus and spin down. So this is all the solutions. The algebra is extremely simple, in fact, no complicacy whatsoever. So you just carry out and you will obtain everything. So these n's are the normalization constants, and you have to evaluate them by using kind of this expression, and you know how to evaluate it. And then if you calculate for all the column vectors, all psi a, if you consider the outer product, actually if you consider the outer product for all psi's, then you see that the completeness condition is achieved. That means psi a, psi b, psi c, psi c, psi d, psi d. You do the outer product, you know all of them will be 4 by 4 matrices. I have not written it, but when you do the inner product, you obtain a number, 1 by 1 matrix, that's a number, and this outer product will give you 4 by 4 matrix, and you add 4 separate matrices, each of 4 by 4 order, and you obtain a 4 by 4 unit matrix. So this one is a 4 by 4 unit matrix. Now, we make a small correction here in the text after we define the normalization constant, how to evaluate it, that n1 square is the psi a dagger psi a, and similar calculation for psi b, psi c, psi d in case of n2, n3 and n4. And we define the completeness condition in this way, as you see it here. Consider the outer product of all the functions, all the column vectors, and in fact all the functions. We proceed to estimate the normalization constant by calculating the term psi a dagger psi a, and we have written the form of psi a here. It is written, and you check that it is px plus ipy. So when you calculate psi dagger or psi a dagger, you write it px minus ipy. Be careful on that, and then just proceed in usual way. Just calculate the matrix multiplication, and then replace this px square plus py square plus pz square by p square, and then use e square, this relation e square plus e square equal to, or e plus square equal to p square c square plus m square c to the power 4. Replace this one to obtain this expression, and finally you obtain your n1 with this value. And if you calculate n2, n3, n4, you will see that all of them are equal, and let them be equal to n, say. And now we check that for p equal to 0, that means we have a free particle with p equal to 0. In that case, its energy E plus will be mc square. You see it easily from here. Set p equal to 0, this p square c square term then becomes 0, and E plus becomes mc square. Note that we are taking the plus term, positive energy E plus equals mc square. And then you use E plus equal to mc square. So you find out this to be 2E plus, and sin, and then your you see that your n becomes 1, and hence your psi a, which you can see from the first expression, here is your psi a. So if you see your psi a here, then this will be 1 0. As p is 0, then this two term, this one and this one also becomes 0. So your psi a with n1 equal to 1, this n1 becomes 1, as we have checked it for p equal to 0. Your psi a becomes 1 0 0 0 when p equal to 0. And we can evaluate psi b, psi c, psi d in a b, c, d or in a similar manner. And then we go on to estimate the outer products of all psis. Psi I means I runs I equal to A, B, C and D. So 4 psis, and we calculate the outer product there and then sum up. Or this is an alternative statement of this mathematical expression, that we are summing over all energy states and all spin values, that is 2 energies plus minus and 2 spin states up and down. So we have 4 states here. So this is the completeness condition, and we will see that when we consider all the positive energy solutions and negative energy solution, the completeness condition is satisfied. I advise you to check it for at least p equal to 0. Now we need to verify, or we need to focus on a very interesting point, that we are considering the negative energy solution for a free particle, which is in common sense very much unexpectable and unacceptable also. In fact, in our classical sense actually, that how can the energy of a free particle become negative? But if we want to discard it, we will have serious trouble. In mathematics, it is a common practice that if some solution, in mathematics and in physics, in fact, actually in physics, it is a common practice that if some solution is unphysical, then we discard it. If mathematics produces any solution which has no physical standpoint, then we discard that solution. But if in this case we go to discard the negative energy solutions for the free particle, we will see that the completeness condition is not satisfied. But completeness condition is a necessary condition because the psis are the eigenfunctions of Hermitian operator. H psi equal to E psi, that Hamiltonian, Dirac Hamiltonian itself, it is a Hermitian operator, and so we know that the eigenfunctions of a Hermitian operator satisfy the completeness condition. But if you discard the negative energy solutions, even for a free particle, then the completeness condition is not satisfied. Therefore, we have to consider the negative energy solutions along with the regular positive energy solutions. This is a very peculiar outcome of the relativistic theory of electron. A very peculiar outcome of the Dirac equation. And now if we can formulate the total solution psi RT, where this part is the, as we have said it before, that this is the time independent part which depends on the momentum, and this exponential part is the oscillatory part of the function. We have 4 psi functions, A, B, C and D, corresponding to 2 energy values E plus and E minus, to obtain the full solution corresponding to a particular value of P. That means if P changes, the nature or form of the solution will change. But we again repeat that with all the solutions, and the 4 solutions correspond to positive energy values as well as negative energy values, which has very important consequence. Thank you.